seconds. Next up, we have Abram Hindle, who will be talking about WebAssembly and Impractical WebAssembly, which I cannot wait to see what that means. So we'll take a 2-second talk again, a 2-second pause again, so that we can isolate it, and then we will get to Abram, and I will mute myself.
All right. Well, thank you for that introduction. I'm here to talk to you about WebAssembly, Impractical WebAssembly, WebAssembly the way you're probably not going to use it. So WebAssembly is pretty interesting because people are trying to make high-performance JavaScript, especially on numeric code in the past, and they're coming up in different hokey ways of doing really kind of tight JavaScript with no abstractions. And eventually they started coming together, come up with WebAssembly. And WebAssembly is basically a binary instruction format that uses a stack-based virtual machine. And it's important that it's a virtual machine because people were very worried about the security of your browser as assembler was run within it. So as WebAssembly.org says, WASM is designed as a portable target for compilation of high-level languages like C, C++, Rust, enabling deployment on the web and server applications. Okay, so this means they actually don't care about you writing it, and they don't care about you reading it. In fact, the documentation for WebAssembly is not for beginners. It's quite poor, and I think that you basically need to be publishing at PLDI, the Programming Languages Conference, in order to make a lot of sense of the WebAssembly documentation. There are some introductory things out there, but they're far and few. Now, during this talk, because it is assembly, a lot of you are probably not super familiar with it, or you know a certain kind of assembler and you're trying to connect it to WebAssembler and you're just trying to figure out that connection. Please feel free to ask questions during this talk. I'm totally open to questions. I really would prefer to answer questions than to give this talk itself. All right, so what am I covering today? I am covering how to write WebAssembly by hand, how to compile it, and the basics of WebAssembly. What I'm not going to cover is I'm not going to cover how people actually use WebAssembly. Most people compile C or Rust or Go to WebAssembly. I don't care about that. If you like to use TypeScript, you'll use something like AssemblyScript, such that you can do WebAssembly in a TypeScript compatible kind of typed fashion. I'm not really going to get into the nitty-gritties of WASM bytecode. I'm not going to talk about what's called WAT without S expressions. And I'm not going to talk about ASM.js, and I'm definitely not going to talk about mscripting. Those are the things that you'll actually use if you want to use WebAssembly. We're going to talk about WebAssembly itself and how you can write it by hand. But before we start, you have to be aware of why it was made the way it was. People are really concerned that if you had full assembler on the web, that you would be able to do things on a machine and get very low-level access. This means row hammer attacks where you're reading memory via statistical inference. They're very concerned about safety. So security is at the forefront of WebAssembler, and it takes a big performance hit because of it. But essentially, you don't want to run other people's code like that willy-nilly, so maybe it should be safe. Also, they want it to be portable. It should run in almost every browser, and currently it mostly does. Furthermore, they cared about performance, but they cared that it was fast enough. Current implementations of WebAssembly are frankly good enough or fast enough. They were also really concerned about loading. JavaScript payloads have been getting really big, and people have been using different techniques to reduce that. So what they wanted was a concise binary format that's easy to compress, that's easy to ship, that's very small, not big like, say, x86 64 or something like that. They wanted a nice, compact representation, and WASM actually achieves that. All right, so before we start, let's just recognize there are certain limitations. WASM made the choice of security over performance. They also made an issue where you can't actually write assembler in the browser. You have to use a compiler or assembler to take your program and convert it into WASM, the binary format, and then you can load that. It's also very difficult to share information between JavaScript proper and WASM. There's also a lack of expected features if you're a programming language designer and you're kind of expecting to compile down to WASM. This means a lack of go-tos, a lack of a visible stack. They use these kind of weird type pointers that you have no access to and you can't manipulate. as well as typically the way you're going to interact with it in JavaScript is through typed arrays into basically this linear memory that they allocate. I'm just going to flip down. All right, so feel free to ask questions at any time. They'll mostly get read out to me, or I'll check them out, and whatever, just ask questions. But I do recommend that you go to my GitHub and you go and get the code yourself and give it a shot. If you go to Abram Hindle, github.io/impractical-wasm, you get these slides, and these slides can evaluate WebAssembly for you because I jammed in the WebAssembly compiler. Normally what you got to do is to take this WebAssembly code, which might look like Lisp to you, but trust me, it's not, is to run WAT to WASM on that file and make a main.wasm out of main.wat. Okay, so this is a text format, WAT, and what it produces is a binary format. Then in JavaScript, what you typically do is you go and you fetch your WAT, you load it up, you jam it into a WebAssembly object, you get its exports, and then you run it. And it does pretty well this. So in this case, it's returning 42. Let's just walk through this program very quickly. First off, we start with a module. Now I define a function. It can be any function. I'm just using main for this presentation just because it's easy to know what I should be running after I evaluate. And then I say, I want main exported such that we can actually call main down here in the JavaScript. I'm going to say that this function returns an I32, so it's a 32-bit integer. And what I do is I call return, and I give it a 32-bit constant. So it returns 42, which is a very special number. All right, so let's boot up. Our module holds our assembly. JavaScript also, that's basically what JavaScript imports. And we can export to JavaScript, but we can also import information from it. So if you want console.log, you can actually make an imports and have it imported into WASM such that it can call it. So that's kind of fun. Now, I'm going to use the S expression format because I love Lisp and I love S expressions and I think that they're great. They're a nice way to show that you have a tree of computation. So the way to read them is that this S expression between these two parentheses is going to be evaluated. It's going to have this as the thing that gets evaluated, and this is its parameter. So this gets evaluated, and then it returns like a constant 42, and then this one gets evaluated, and it's going to return that constant. So it's basically like a tree of your program. You don't have to write it this way, but I'm not going to write it the other way. The other way is to not really use S expression structure and take advantage of the fact that WASM is a stack machine. This is really annoying. So what we do is we push a constant onto the stack, and then we push an opcode onto the stack, and there's nothing really left on the stack. So what it does is it says, okay, the first available opcode I see is a return. So it runs that return, and then that return pops that 42, and then the return does its business, which is returning a value. So it popped the 42, and now it pushes the 42 onto the stack, such that anyone who wanted the output of main will now get this integer 42. Fun. This gets more complicated when you have opcodes that have more than one parameter. So yeah, we're going to stick with the S expressions because they make sense, whereas these are a lot harder to use. You do get better control of your WASM if you use this kind of format, but you're writing WASM by hand. You need all the help you can get. So we'll just stick here.
Abram, we have a question.
Yes, great.
So the question came up from Stephen Myers in the chat that this doesn't really look like what you'd expect from traditional assembly.
Right. It's mostly because it's assembler for it's not traditional assembly because it's assembler for a virtual machine, a stack-based virtual machine that has hidden memory from you that you can't access. So it gets really strange. And it even provides you a lot of abstractions that typically you'd have to do yourself in traditional assembler. For instance, the function, no one ever provides you with this one. Sometimes the CPUs have a little bit of help for you. They've got a return where they deal with the function call frame on the call stack, and they can return from your function with a value and all this kind of stuff. WASM does it for you. So they do provide some abstractions, but it's such that they can have a really tight, small virtual machine that can run it pretty fast. So I hope that answers your question. It is definitely a very high-level assembler. All right. So we're just going to get into it real fast. So we're going to quick boot. So to export a function, you have to call export at some time. You can really jam these right immediately after you define them. So here I use a $sign to indicate a symbol, mainly main, and then I say export it as the string main. Okay, this string will actually show up in the compiled assembler. And then I say it has a result, and then I have the code. If you don't export the function, your JavaScript won't see it. All right, let me just check real quick. Advent code. Right. Okay, good. All right, next up, the function. How do we make a function? Well, we have the func opcode, and the func opcode is not really an opcode, it's a definition. It allows us to define a function, and it will set up all the data parts for us that we need. We give it a $sign symbol name. We can export it immediately after. We don't have to. If we don't export it, JavaScript won't see it, but maybe we don't want JavaScript to see it. For every parameter, you go param, and you give it a name like $X and then a type. You always need a type. This is what's really interesting. WASM is type checked and fully typed. If I use F64, a 64-bit float, instead of I32, and I try to jam that in there, it won't compile. It'll complain because it's statically type checked it, which is pretty cool. We also have the return value. So this is kind of backwards compared to how you normally write Java or something, or C, but it works mostly good. And then after this, you have all your little S expressions, which will be the function body. Okay, so that's a function. And so here I've got a demo of basically defining a function and calling it. So functions are great, but they're only great if we can actually use them. So in this case, I'm making a function I'm not exporting. It's called func with arg. It has one parameter x, and all it does is it just returns x. Okay, so in order to access
another question.
X, great.
So that function returns an int32, but JavaScript can't represent 32-bit ints. How does that work? Does it get converted to a double?
A double can represent a 32-bit int pretty well.
What happens?
So,
what
but
happens if there's a type mismatch?
Oh, when there's a type mismatch, your WAT compiler will complain bitterly, and it won't make a WASM file for you. So you'll see the error, and you'll have to debug it. So it will type check for you. Yeah. But back to the first one. Yeah. So, okay, I forget the first one. What was the first one?
The first one was about 32-bit integers converting to doubles.
Oh, usually that's not a huge deal. Doubles have about like 48 bits of mantissa, so they can hold a whole 32-bit int. There is problems with it because you have nans and things like that, and you also have negative zeros and all that confusion. That is a problem. But the other way of dealing with it is to use typed arrays. So if you're really concerned about type coercion, use typed arrays. Okay, I think I got it. I'll continue on with this example. In this example, I have two functions defined. I'll just evaluate it. And what I do is I've got getLocal here, so it just returns this value. Notice how this function returns something without a return. That's another cool aspect of WASM, and from a Lisp user like myself, I really enjoy the fact that the final expression is returned. Essentially what happens is if there's any values on the stack after the function returns, it returns that value that's left on the stack. So when we run main, what main does is it has to call the function. We can't just go $func with arg, so we have to use the opcode call. And what call will do is it will look for the definition of func with arg, and then it will call it with the parameters, and that will all be on its own private stack that you don't see. So the call stack and the stack that has these values, like getLocal, you don't see, but it's going to mess with it, and it's going to call func, and it's going to have the parameter, and you can go get that local. So in order to call a function, you need to do this. I tried getting this value, and I think this is like a function type, and I can't resolve it into like an integer value. So I don't have access to this. If you need integer access or functions accessed by integers, you can make a func table, which I'm not going to talk about in this talk, but it allows you to be very dynamic with your functions if you need that. So it is available, but it's fully typed, which is interesting. All right.
We have another question about variable types in this case. You can't write a program with just integers. Is there strings or pointer arguments in this level of assembly, or is this all just ints?
Well, I think C would argue with you that you can write everything with ints just perfectly fine. In fact, you should come and check out the code from my Compute 201 course where that is demonstrated repeatedly. But yes, there are multiple types, but the types are going to be just different kinds of integers. So you can use smaller integers, but you only have I32s to work with. You can store and load 8-bit integers. You can store and load 16-bit integers. You can store and load 32-bit integers and 64-bit integers. You can do math on 32-bit and on 64-bit integers, but they don't have a lot of specific 16-bit and 8-bit integer opcodes. So you can do byte manipulation all you want. There's no character type, there's no string type, and there are 2 floating point types, float 32 and float 64. So this means that when you jam in a string into your WASM, you're really going to write a bunch of bytes into a shared uint8 array, and it's going to read it, and you're going to communicate the size because we're not going to null terminate the string unless you used C and you're doing LLVM and all that jazz, and you do have to do it. But typically, if you're writing it by hand, you don't have to null terminate anything. You can communicate the sizes. So I think I answered that question. Your types are ints and floats. And if you want smaller stuff, you can use smaller loads and stores. So it's kind of kludgy. I don't really like it. All right, to call a function, you need to use call. It uses a symbol to refer to that function. This is properly type checked that it is a function. I assume the function arguments are called by value such that they're copied onto a stack. You do not get access to this call stack, but the arguments are type checked. So this is a nice type checked assembly. That's kind of cool. I'm going to click eval on this one, and it's going to show that it returned 22 because I just jammed 22 into this function. So it ain't that special. All right, so off to the next. So that was pretty cool. We can do that in the browser, right? No. Actually, I had to do a little gong show here where I linked in libwabt to compile WASM in a reveal.js slide deck. It does work, but on your computer, you typically will compile using WAT to WAT-B, and that's from the WAT-B project, and it'll compile it for you. But if you want to do it live on the web, you have to use libwatb.js. And that is some mscripted mess that got compiled. It looks really bad. It's like unreadable because it's kind of like WASM. So we've got this little program. What does it look like? Well, if I run wat to WASM on it and I tell it to be verbose, we can see it gives itself a little version number and a little type code. And then it starts a section. And it says it's got a section and how many types it's got. And it's got 2 types because we got 2 functions. And their first function has 1 parameter and it's got 1 result. And our second function has 0 parameters because it's the main function, has 1 result. Okay. And then we go to the section of the function and we can see that it basically is just data that describes the function. And then here is the second function main, and it has an export name and what kind of export it is and what its function index is. So this is just data about the function. This is not operational. This is used for linking and loading. Next is code, and it tells us how many functions we got. We got the first function here, so this is going to be func with arg, and it's got local decal count. It's got get, and it's got the index, and it ends. All right, so it runs get. and that'll be on the stack when it runs, such that when main runs, we can see that it pushes, it says that there's a constant, it puts that onto stack, right? And then it calls it, all right? And then we got the function index and we're done. So it has this left on the stack, this value that we got in here, which will be 22, right? Which is, that's 16 plus 6. So 16 plus 6. So that's that value there. I don't want to write this stuff. This stuff is gross. You never have to look at this stuff. And this is simply a textual representation of the actual binary that it runs. Ain't that fun? Okay. So it looks like that. That's not fun to work with. So we'll stick with WAT and S expressions. But we're stuck with the memory model. WASM has a stack and it hides it from you. This stack contains values you pushed on it and some function call frames that you can't really see. What you can't see is function locations, function code, parameter locations, locals, or the location of locals. So you don't get access to this stuff. You don't get access to your stack like you do in C, or if you wrote assembler by hand. What you can see, though, is you can allocate as many locals as you want, and you can define as many functions as you want. And it will handle function calls for you just peachy keen, and it'll handle calls to imported functions just fine, which is really nice. And you can access some explicitly allocated memory, like a heap. And you can even grow the heap if you want. So it's kind of flexible, but it's very different. Now, I was already asked the question, what data types does it have? It's got 32-bit ints and 64-bit ints. And it's got 32-bit floats and 64-bit floats. One of the problems is if you use 64-bit floats or 64-bit ints, how are you going to get them out? The answer is you usually use a typed array and you write to memory. There's no real good way of getting a 64-bit integer out of WASM other than writing to memory and then reading it from an array buffer. That kind of sucks. All right, I'll just check if there's any questions. All right, looks good. I'm totally willing to answer questions, and please ask them, because it's probably pretty easy to get lost. All right, so we're going to talk about instruction and opcodes. Typically, instructions consume 0 or more values off of the stack, and often they push a value onto the stack. Not all the time, but sometimes. And you can't really access the stack directly, but you can push and pop to it. So first and foremost is, how do you make values? Well, .const. And you prefix .const with the data type that you want. So here I've got 64-bit floats, and I'm going to multiply 2.0 times 10 to the minus 9 times 2.1 times 10 to the 10. We're going to evaluate that. Oh, 42. Imagine that. Here's a 32-bit integer. We're going to multiply our 32-bit float. We're going to do the same calculation. It's kind of close, but that mantissa is not as big, that's for sure. Now we try with the 64-bit integer. Type error, cannot pass I64 to or from JavaScript. Great. Okay, so watch out when you're using 64-bit ints. But it works perfectly fine on 32-bit ints. So, we used hexadecimal to represent the integer. We don't have to, but when we evaluate it, we can see that's multiplying 255 by 65,536. Yeah. All right.
Possible question. This has got a lot of people excited. So Byron Hill in the chat has asked, what's a good project for a practice thing to start using WebAssembly?
I would choose something that has that likes integers, that likes typing, that likes pooled memory. So a hash table, or a special kind of hash table, or maybe like naive Bayes with a hash table. So you're basically storing counts of, say, like n-grams that you saw, like 4 character or 4 byte grams, and you're counting them. So you could use that for spam detection or something like that. That would be if you're doing WASM by hand. Most people, what they're going to be using WASM for is they're going to be taking an existing program that is compiled, like a Rust program or C program, and there's maybe a function in there that they like, and they want to compile it to WASM such that they can call it from JavaScript and use that. I've seen this done a lot with OpenCV or computer audio code, where you're generating like a little synthesizer and you don't know how to do it in JavaScript, and the code's already there, so why not use it? I think that answers the question. Those are my suggestions. Okay, I'll just check the thing real quick. Mark asked something about SIMD. Later WASMs do support SIMD, but it's not clear it's in the browsers yet. Some of these features will be later. But there is no, I haven't seen anything with the current WASM 1.0 where you can do anything in a vectorized manner. So there's problems with that. Yeah. But if you want to work with 32-bit integers, I really think that WASM is probably for you. It's good stuff. Like if you really want to be right on about 32-bit integers, you don't want any coercions, WASM is a good way to verify, or, well, yeah, to verify that you're staying in 32-bit int zone and you're not casting up to a double anytime soon. So that's kind of good. All right. So you got lots of arithmetic in WASM. It does numbers okay. It has things like addition, subtraction, multiplication, division, unsigned division, signed division, unsigned remainder, signed remainder. So with the floating point numbers, add, sub, mul, they're all normal. But with the 32-bit and the 64-bit integers, you will have sometimes unsigned and signed versions. So here I've got a 64-bit addition, and I'm going to add 2.0 times 10 to the 1 times plus 2.2 times 10 to the 1, and oh, look, 42. Imagine that popping up again. Here I've got a 32-bit multiplication, a 7 and a 6, and oh, same number. It's almost like it's hard-coded or something. And then here I've got a division. This is a signed division, and I'm dividing 1024 by 24, and this will be integer division. Can you guess what number it's going to be? Well, I'll just click it. You know what number it's going to be. All right. So that's signed division. We can use unsigned division, and you should only really be using unsigned division if your integers are unsigned values, because treating signed values as unsigned is problematic. Okay.
What about exports? We have another question from Stephen about how would you write to an array buffer? You mentioned that earlier. Do you create the buffer? Is this like a malloc?
I will cover that in detail later.
Excellent. Look forward to that.
Yeah, heavy detail. Let's see if I can push through it. Okay, so we've got to ask questions about array buffers, but first we have to deal with locals. So to make a local variable in a function, you, at the top of the function, not during the function, only at the top, you declare variables local by local, the symbol, and the type. So here I've got local $i32. And because of safety and security, they are going to initialize all your locals, usually to 0 in both cases, positive 0. So local $i32. To access I, we can't just use I directly. I is basically a symbol. So we have to go get local $i, and we can set local $i, and we can set it to a value. Okay, so what are we doing here? We declare the local, and then we go get the local, add it to 42, because that's what all my examples have, add it together, and then return it. So I'm going to eval that, and we can see that it was initialized to 0, because 0 plus 42 is 42. All right, maybe I should use a different number, but just kind of felt that way today. Now, you got a function, and that's cool, but let's not do conditionals just with numeric operations. We have actual conditional operators such as if. And this is where it gets really different, because typically in assembler, you don't have access to an actual if. Typically, you do a comparison, and then you jump if not equal, or you jump if equal, or jump if 0. So they provide a whole if to you. So your if, first you do a comparison or math. So basically, is it 0 or is it not? So what we're doing is we're getting the remainder, the unsigned remainder of x divided by 2. Okay, so this is like x modulus 2. And we're going to do this in a function called even that takes in one parameter. All right. And then on this, we're going to return minus negative 1024, and on this positive 1024. So we're going to jam in 42, and we're going to see what the result is. And we can see that the result of 42 was that this would be a 0. So that meant it took the else case and returned 1024. Okay? Fun stuff. Also, another cool thing is we do have the ability to return at any time, which is pretty powerful given that some scheme languages do not allow such kinds of returns. I have a return value here because I said we'd have a return value. And without declaring a return value on the if statement, it's not going to let me just leave it be. It's not going to do the analysis to figure out there's no way out, which is annoying. But we can make the if statement return a value because we love ternary operators. Who doesn't? And how do we make an if statement return a value? We say that it has a result. We say it has a result and it's got a value. And so using the same thing, I no longer need those extra return statements, and I'll just put in 41 instead of 42, and you'll see that it returns a negative 1024, which meant that it hit this one. So isn't this cool? You actually get an then and an else in assembler. Doesn't really feel like assembler, does it? It feels just kind of atomic and low-level Lisp, you know, kind of weird. All right, let me just check if there's a my face when ternary operator. Good joke. All right. So it also gives us loops, which is nuts because typically loops are a real pain when you're writing assembler by hand. When you're writing assembler by hand, usually you got to put down a label, and then you got to do the body of your loop, and then you got to do a comparison, and then you got to jump to it. Well, they get around the loop label issue and being able to jump back to that loop label just by giving you a loop opcode. And this is a real opcode. This isn't syntactic sugar. And the loop will basically run everything inside of it. And if you jump at the end of it, you'll jump back to the start of the loop. So let's look at this code right here. I start off with a local. I is set to 0. I set the local to be I plus 1. So we add to I, we add 1, and it'll do that. So will this do an infinite loop? No, it actually just returns 1. Why? Because there's no jump statement here. There's nothing that tells me to go back to the top of the loop. We actually have to do a jump for it. And it's not a jump, it's called branch, which is kind of weird because, I don't know, I don't like the name of it. But if you run branch, you can jump to either a label or you can give it like a 0 or a 1 or a 2. 0 means the current local block. 1 means the enclosing block. 2 means the enclosing block. Or the label, which I assume is a type, you jump to that block label. Here we've got a loop and it doesn't have that block. We've got set local from the last example. And now we've got an if statement where we use a comparison operator called i32.eq, which means 32-bit integer equality. And we get two integers, I and 1,000, and we check to see if they're equal. If they're equal, as in we've counted up to 1,000, then we return the value of I. Okay? Otherwise, there's no else on this, so the next thing running is br0, and br0 will hop back to loop, and it'll keep running. So this thing will keep looping. Okay? And then I put get local I down here because I promised that the function would return a value, and the loop didn't necessarily do it, so whatever. And we can see it did it 1,000 times, so it ran through 1,000 times. Pretty... well, it's not super simple, but once you get the idea that the first argument to the if is going to be some kind of comparison or some kind of math that's 0 or not 0, then you're good to go. All right. So sometimes we want to do more than just breaking out of the loop. Sometimes we want to carry on with our function. Sometimes we don't want to return from inside the loop. So if you want to branch, there is a conditional branch called brif. And brif, you can give it a 0 or 1 to tell it what to do. So it's saying branch to 1, that is this block here, if I is equal to 1,042. Okay? And so we run that, and we can see it counted up to 1042, returned that get local, and the return value is right here. So it actually got to the end here. If this is not true, it's just going to fall through, and we're going to run br0, which is just going to keep doing this. But I can only do br1 if there's an actual block here. So if I have a loop here, or this thing called block, which is another structure you can use. Block is it's just a block of code that you run, and you can even put a label there so you can hop to it. That's how you hop around. And blocks are the only way you're going to get around the lack of go-tos, because you can hop to the block that you want. So here, we've named the blocks. I got an inner and outer, right? Kind of like belly buttons. And what we're doing is we're just looping. This is an infinite loop. So it'll just keep hopping to the top. And then this block is the inner loop, right? And what we'll do is if we hit 1024, we will say we'll branch to the outer. And now because this is a block, right, and not a loop, it's not going to hit this. It's actually going to hop to the end, and we're done. So we can hop out by basically jumping to the end of this label, which is really strange. Okay, so you have something like a go-to, but it's totally not a go-to, and it only works with really local labels, which means that if you're writing a language that likes continuation passing, that likes parallelism, that likes generators, that this WASM stuff is going to give you a headache. And the Go community is really kind of annoyed that WASM is designed this way, because it really slows down Go compilation for WASM. It's quite complicated. All right, so that's branching, and that's as close as go-to as you're ever going to get. So we got BR and BR if. There's comparisons. You can do less than, greater than, less than equal to, greater than equal to, equal to 0. And you can jam I32 or F32 in front of them. There's also signed and unsigned versions of each one of these for the integers. So be aware of those. And the comparisons are really they just push a value onto the stack. So here's equal to 0. So we've got main, we got a local, and we check to see if the local is set to 0. If it's set to 0, we return 10,000. We got 10,000. Here's sign greater than. So I32 GTS, we compare them -1 to 1. Is -1 greater than 1? No, it's not. So it's going to return -1. Okay, that's cool. What about this one? I32 greater than unsigned. -1 and 1. So which one is it actually going to return? Is unsigned -1 greater than 1? Well, we'll just evaluate since question and answer is so slow. And it is. Why is unsigned -1 greater than 1? Well, because unsigned -1 is 0 FF, 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 and unsigned 1 is 0, 0, 0, 0, 0, 0, 0, 0, 1, right?
So why was branching designed that way then? If it makes it purposely difficult, is there like a reason why it was designed that way?
The reason is typically for program analysis. So it's important to understand that JavaScript runs fast because of the power of JITting and program analysis. And one kind of program analysis called SSA works really well when you don't have arbitrary go-tos. So out of optimization reasons for some kinds of programs and some kinds of analysis, it is great not to have a go-to like that. That's about it. So, they kind of are harming performance of certain languages over other languages. But with the ability to analyze code, they probably can figure out ways to analyze the code that had to do hokey things to get around this hokey limitation. That's my impression. All right. Okay, so we'll just kind of breeze through this stuff. I think we're getting pretty close. I was asked, how do we communicate arrays? How do we communicate multiple values to WASM? Well, one neat thing is that we can make a memory object, a WebAssembly memory object, and we can import it. Okay, so we can import it or just have it in WASM. We can allocate pages, and then we can store values into those pages and read them out. So if you wanted to read in 32-bit or 64-bit integers, you'd probably do it through this manner. So this is basically you making a heap and accessing it. The weirdest thing about this is that you'll have address 0 being a legitimate address that you can manipulate, which any C user will immediately shudder and realize that if they are compiling a C program, that they probably shouldn't operate within the first page of WASM memory just so that they can avoid various bugs, or at least the first kilobyte, like. Anyways, so let's take a look here. I've got an import statement saying I'm importing it. So I'm importing env memory. But what I'm really doing, just in case, is I'm saying we have at least one page of memory. So memory now exists. So that means we have one page at least. So we have 0 to address 65535. So 64K. Then what we're going to do is we're going to go 64-bit store, and we're going to store at address 0, which is like danger zone, but whatever. We're going to store this floating point number. And then I'm going to load that floating point number and return it. Okay, so let's see. Yeah, we got 0.42 out into JavaScript, even into a web page. Amazing. But it was at address 0, which is scary. Makes me uncomfortable. So how do you do arrays? Well, what we'll do is we'll ask in JavaScript WebAssembly to make us some memory. So this, I'm asking for about 65K, I think, or 65 megs, I think. Yeah, 65 megs. And then I'm making an import where env memory is there. Look at that env memory. It was all back here, env memory. And now I'm basically getting my WASM. I'm instantiating it. I'm getting my exports. And then I'm making myself a float64 array. And lo and behold, what do? I pump in buffer. That's from this object here. So that means this has an array buffer that is now shared. So anything that I write to it is now shared between WASM, and, well, at least this WASM module itself, and JavaScript. That's kind of cool. Now, can I put in float60? Can I put in typed array, or can I put in memory buffer as an argument into one of these WASM functions? You can, but it's not going to work. So typically you put in a pointer like 0. Okay. If you don't want to start at memory address 0, you'll put a different number in right there. Okay. So we're pretty far. All right. So I demoed. I got into WASM because I thought I'd get some good performance out of it, right? I thought that would work. So I made a summation function, and if I click here on the sum, we go over here and we see nothing showing up because this was not made for presentation, I'll tell you that. And so I'll just reload this. And so it took 300 milliseconds to load the SUM.WASM, or load SUM.WAT and compile it and then link it. Then it took my JavaScript WASM over that array buffer. It took it 300 milliseconds to do a summation over all those elements many, many times. So for the one array, it can do the summation in about 30 milliseconds. My basic WASM took 44 milliseconds, and my good WASM took 23 milliseconds. So it can be faster or it cannot be faster. I will go and show you what my summation looks like. So here's my summation. And the first one uses this function called offset. And offset is going to calculate where in the array should we hop to. Okay? And because we're using 64-bit floats, what we have to do is we have to multiply 8 by any index into that array. and we got to add that to the location of the start of the array. So offset just basically produces the array offset. It doesn't actually read the array for us. So here's our first ASM sum. So all it's going to do is going to take a pointer to an array. It's going to take how many elements from that array it should summate, and then it's going to return a summation. So I've got iterator I, I've got output O, I set I to 0 for no good reason, I set O to 0.0 for no real good reason, they're already initialized, and then I have a loop. And loop basically loads at every offset that value, okay? So it basically keeps loading each consecutive array element, and then it adds it, and it stores it in O, and then we iterate. We add 1 to I, and then if we're at N, we quit. Otherwise, we loop, 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 loop. Eventually, we return our sum. Okay, so this one uses a function call to calculate an offset, and this sum2 does not. So you see this thing where the load? In this one, I've inlined that with no function call. Okay, so this one's pretty fast, looks like garbage. Let's go look at the results again. In Firefox, by inlining that, I saved quite a bit of time, significant time. Let's go look at it in Chromium. All right, here we go. I'll rerun this. And we got 26 for straight up JavaScript, 67 for WASM with calls to offset, and 40 milliseconds for WASM to the inline WASM. That's kind of weird. I don't really like that. So let's go look at what my JavaScript one was. So the cool thing is I can communicate to WASM with JavaScript by writing to this array. Here's my JavaScript sum. So we just start with 0, we go through, and we add. Pretty easy. And then how many repetitions do we use? We use a lot. I'm iterating over 10 million times, and we do that 10 times. So the arrays are quite large, and we do it 10 times. All right, so it can be faster. It might not be faster, and it depends on the browser. And frankly, I think my Chromium got slower because when I ran it last week, Chromium was faster. So I don't know. All right, let me just check for questions on that one. Doot and do. All right, question. Do you think a compiler like Rust would inline the function for you? I sure hope so. Function inlining is probably the biggest gain you get from WASM. So probably that's really what the compiler gives you, is the ability to make that code less annoying. The fact that you're writing your own WASM function, you're directly using call, indicates that you're going to be relying on that thing to be faster. And it might not be faster for you because it's going to have safety checks in there. So that's a good question. Let me see. Okay, so you declare buffers, then you call WASM, then it writes to the buffer. Yeah, so you can declare your buffers, you can call the WASM, you can write to the buffer, you can also write to the buffer before you call WASM, and you can even read from the buffer after you call WASM. And then there's new extensions that allow you to have a shared buffer between both of them. All right, so let's see. Performance, it depends. My Firefox was pretty good. My Chrome was really great for JavaScript, not so great for WASM. It's kind of, you know, but none of these are really horrendous. None of these are like, I don't know, over 4 times slower or 4 times faster. So that's fine. That's fine. So I was thinking, that was just summation. That stuff's easy. That's like SIMD garbage, easy peasy. What about something that's actually computationally intensive, like a recursive function like the MANDELBROT? So the MANDELBROT function is a function that you call many, many times, and when you find that it's not converging anymore, you quit. Or something along those lines. So you've seen MANDELBROTs before. They look really pretty. These are 4 of them that just drew because I programmed them in JavaScript and WASM. These MANDELBROTs took 81 milliseconds in pure JavaScript going pixel by pixel, or 181 milliseconds, 170 milliseconds calling assembler WASM, and then putting it all into JavaScript and not leaving and not like iterating over every element in the buffer and not calling a function to actually calculate the function. It took 170 milliseconds, and the WASM Mandelbuff took that. On Chrome, let's just take a look at Chrome. Bada bing. Chrome is all over the place. So its JavaScript Mandelbuffer is great. It's 178, and its WASM one is awful. It's 275, but it's still not on the order of 2 or 3. So I'm not willing to really bag on it too bad, and it can always improve. Now, I'll show you what the code looks like. I hope it makes sense. We're going to start with the JavaScript, to be honest. So first off is the JS Mandel function. What this function does is it does the Mandelbrot function, which is basically Zn equals Zn minus 1 squared plus C. C is your original point. It's your XY coordinate in the complex plane. And then Z0 started at 0. Complex numbers are basically tuples, one in the real domain, one in the imaginary domain. So it's really just like 2D positions. Anyways, what happens is we keep repeating this calculation over and over and over again. And if we exit a certain space or we hit max iterations, we just quit. Okay? So the less iterations you have, the more likely that you're not within the Mandelbrot. If you're spending a lot of iterations, you are within the Mandelbrot. Okay? And so that's how we do basically every single pixel of this pretty Mandelbrot picture. Okay, I'll make it big. All right? So let's look at how we do that in assembler. So first off, we write the Mandel function, right? And it's got a lot of locals. Okay, we've got our iterator, we've got our complex numbers, zx, zy, and the squares of those numbers. And then we do all the annoying math. So we set zx, we set zy, we set zx. So we do floating point addition, multiplication, and then we square them. And even squaring looks awkward. It's the multiplication of 2 get locals. And then if it's, we branch if it's equal to max iteration, or we branch if it escapes the Mandelbrot sphere itself. Okay? Then we also do the drawing each pixel in assembler. So we have a while loop. So this is for per row. And then we have a column loop, so for x value. And we calculate what the location is, which is just this calculation, something like that. And then we do a call to our Mandelbrot right here. And you can see this is why it's really annoying. Now I want to show you this stuff. I was asked, can I use other data types? Yeah, you can. So here we're doing 8-bit storing. So I'm storing 8 bits at a time. I'm storing red channel, green channel, blue channel, and alpha channel. All right. So it stores all that, and we get the Mandelbrot. What does that ugly code look like in JavaScript? Well, we'll look at, where is it? Draw Mandel buffer. We get our canvas. We get our image data. We do it as a array buffer. And in this case, we're going to be using a 8-bit integer buffer. And then, where is it? Here it is. This is our JavaScript that writes to the buffer. So we're really just writing to pooled memory. We calculate the Mandel result. We clamp it down between 0 and 255. We set our RGB all the same. And then we set our thing. So you can see that this is pretty small. Writing assembler kind of sucks compared to this. And this is fast too. So then when we run it, what we get is we get some pretty Mandelbrots, but we can see that there's not a huge difference in performance between both implementations on both browsers. In fact, JavaScript Mandelbuff typically dominates. So JavaScript's really beating the web assembler out right now. So that's kind of interesting. So where does performance in JavaScript come out of? What do you usually get out of it? Well, it can improve in the future, but I think most of it comes from the productivity of you using that old Fortran program, you compiling it down to WASM and being able to call it client side on the web. You know, maybe you got some computer vision stuff. You compile it down and you know it's going to be no better, no worse than JavaScript. So that's cool. And you get those advanced functions that you couldn't find in NPM. So there's some real value there. But really, I think where WASM will shine is that the binaries are pretty compact. So you'll likely have better, faster load times compared to straight out JavaScript. So if your metric is essentially, can I do the computation, show it to the user immediately, and the code size is quite large in both cases, WASM might win out. So that's where you might actually get your performance increase. What should you look into for WASM? Well, you should consider using LLVM to compile C to WASM and script them. You can also use Rust and Go to generate WASM for you. They have WASM backends. Conclusion, should you use WASM directly like I did? Probably not. Is WASM useful? Yeah. If you want to do integer stuff in JavaScript safely, probably WASM's the right way to do it. Yeah, if you want to compile other languages such that you can use them in the browser. Does it perform well? Yeah. Not super awesome. Not like you're thinking, oh, I'm handwriting assembler, it's going to be way better. Not necessarily. Not necessarily. It's fine. Is it worth the effort? Most cases, probably not. But I suspect the big gain is from using a real compiler. Do people use WASM like I've been demonstrating? No. I just wanted to know what WASM was. Like, what was it actually compiling down to? What was the virtual machine? Most people are going to use a high-level language or almost high-level language and generate WASM from that and use that. Okay? And there's a lot of good resources out there. So if you want to do this but more, Justin Lim has WebAssembly MVP tutorial. There's WebAssembly by example. These people also use like Rust and other things. The MDN spec is okay. The WAP project is what you're going to really need. This Colin Eberhard, he does a ton of fun WebAssembly by hand, and he explores more modern features of WebAssembly. And sometimes, you know, you just want to see a list of opcodes. This list of opcodes is peachy keen and super cool. I really like it. It even tells you the opcode value, and you can see the opcodes are really small. They're like 1 byte. And it gives you what happens to the stack. Like this one says, 2 32-bit floats produce 1 32-bit float on the stack. Pretty handy, very terse and concise. And you get to see everything that you've got access to. All right, so I think I'm going to come back to the questions. All right. I think I'll switch to something that's less confusing. We will go to space. All right. Question. What does runtime error look like if you, I got to move this over, if you call it JavaScript with a string? You get an error from the WebAssembly object, and it'll show up as an actual full-out error. So it'll show in your console. Yeah. It's kind of annoying. Oh, the other thing I do recommend is at the end of my slides, the last page is a live demo where you can try WASM out for yourself. Or it did work. Don't know why it's not working now. All right, whatever. But you can try it out for yourself, and if that doesn't work, you can go use this demo that someone else got that shows you everything. Not sure why the slides don't work. Anyways, I'm going to come back and answer questions because it's getting late. All right. I think it'd be cool to write business logic, state management, and Rust, and then you could share it. Yeah, Rust would be a great way to do it, and you could maintain the binary format really easily, and you wouldn't have to write a decoder on multiple ends, or you could use something like one of Google's things, like the I forget their efficient binary protocol, protobuf or something. You could use the protobuf bindings on both sides without any problems and without having the right for multiple languages. So there's real value there. All right. Examples of WASM used in production. A lot of games. Games were doing stuff like that. The C-Sound community uses WASM heavily. They also use this other technology called PNACL, but PNACL is going to go away. And so they're compiling to WebAssembly. So there's a lot of people who do like live audio coding on the web for performance reasons, like performing to an audience reasons. So they do like algo raves and live coding. And that's where there's a lot of old audio code, and a lot of that is shown up there. So any kind of signal processing on the web oftentimes will have this stuff. I know that my colleague Nathan uses WASM and Inscriptum. So he does Inscriptum to WASM for his C++ code. And he's even got like a kind of cross-platform GUI where he can compile a bunch of his heuristic search examples, and it'll work, you know, off the console with a graphical GUI, and it'll also work in the browser. So it's pretty cool. All right. Yeah, so OpenCV for WASM, that's really what you would do. Mark has a question, or all right, I'll do Mark's question. Do you think WASM will ever work with garbage collector? It kind of does. So it handles its own stack. So in that sense, it is kind of working there, but I don't think you're going to get access to the JavaScript objects anytime soon. What people will do when they want to interact with JavaScript and the JavaScript GC with WASM is they'll make a malloc routine on their own, and that will be imported from JavaScript such that you will allocate in JavaScript and have some weird WASM access to it. So if you want to send in like a dictionary or an object into WASM, typically you're going to make an import object for JavaScript. So if you really need to walk objects in WASM, you're going to make a bunch of little handlers in JavaScript that will be imported such that you can walk them. And that will probably be very slow and annoying, but sometimes you just need that data right now, so just do it. All right, there's another question.
Cool. I think that's our last question. So thank you, Abram, for a fantastic talk. There was tons of questions during it. I know you've ignited a fire in some of the people here for checking out WebAssembly and being thoroughly impractical on the web, which I think we can take a little bit of inspiration from in our personal lives as well, just to be a little bit more impractical.